Welcome back to CST432 Microprocessors and Embedded Systems. Today we look at Handle with Care. Some of the key concepts we'll cover in this module include I/O categories, I/O processing techniques, nested interrupt processing, and we'll look at the example of the NxOS-Armdebug interrupt handler. First, something about I/O categories. We can define various input and output categories into non-real-time and real-time categories. Non-real-time are started by the application and the response time is not important. Whereas for real-time I/O, it is usually interactive, and for users, they will detect a response time if it is greater than 100 to 250 milliseconds. So, we would like to have response time that is less than this amount to be virtually instantaneous to the user. The device response time, however, is a factor of 10 lower, such as from 10 millisecond all the way down to 1 microsecond in terms of the required response time. And by the way that the system responds to the events that it has to deal with, we can either classify such systems as soft real-time or hard real-time systems. So what are the I/O processing issues? First of all, there is the need to access various registers. These are the Control Command Register or CCR, as well as the Control Status Register or CSR in the peripheral device itself. Secondly, depending on the I/O architecture that we're using, whether it is memory mapped or I/O mapped, we may need to use different instructions for accessing those registers. Finally, we look at processing technique, including polling, where we would read the registers through program control, or interrupt driven, where the change in one of the values on the registers will trigger an interrupt to the microcontroller. How does polling I/O work? Well, first of all, polling I/O is very easy to implement because it involves the CPU and writing a program sequence in order to access the input-output register from memory program. So the disadvantage of using polling I/O is that it wastes processing cycles because the CPU is involved. So the sequence that you show here is an example of how it will work. First, an I/O command will be sent to the CCR of the peripheral to initiate some I/O processing. While it is not done, we will then read the CSR of the peripheral until the status that we read indicates that the I/O request is completed. If it has been completed, we will then exit from this loop. Otherwise, we will continue looping and waiting until the status changes. We may even find polling being used at the kernel level. This is usually needed for a time-critical I/O sequence that must satisfy certain timing constraints. And only we can satisfy this timing constraint is if the kernel or CPU is involved in performing the I/O command and checking the status in real time. Now, the response time of a kind of kernel level polling can be calculated upfront, and we can know how long these requests for the I/O can be completed. Now, unfortunately, if we are using an interrupt handler, we should really minimize such polling because this will tie up the CPU and prevent the processing of new interrupts. Here is an example of kernel level polling. We shall look at the LCD SPI driver in NxOS. In this driver, the set TX mode command will actually program a value into the command register of the SPI bus. So initially, we would need to check whether the SPI peripheral is ready to receive any command. And the way this is done is inside the while loop, we will examine the value in the AT91C underscore SPI underscore SR, which is status register for the SPI bus, to determine whether a certain bit value, which indicates that the transmit buffer empty, is ready, is set. If it is not, we will continue waiting. Now, this value is found in the peripheral memory space, and it is called a volatile memory location because it will be updated by the SPI bus peripheral hardware. Now we see here another example of the kernel level polling. Here in the SPI write command byte function, first the routine will set the TX mode using the previously discussed example. after which we need to wait for the transmit register to empty, and this is again accomplished using a polling loop using the while loop to check whether the 8091C_SPI_TDRE flag is set in the status register. If it is not, we will continue waiting until it is, after which then we will then issue the command to the SPI bus. So this is a timing critical sequence that probably will be called from an interrupt handler, and this is one example of polling in the kernel level software. Now most of the time we will encounter polling in the application level. The reason is because most input processing application level cannot install any interrupts directly or easily, and it is a security risk for the kernel to allow an application to supply interrupt handlers, because potentially we can breach the kernel level security and allow malicious software to install any interrupt handler as they wish. So typically most kernels disallow the installation of user level interrupt handlers. So in such a case, the only type of interrupts that can be installed at the application level is the event timer interrupts that can be programmed to trigger an event when the timer expires. We shall look briefly at an example of application level polling. Here, this is the collect samples routine found in the tripod thumb program. So this collect samples routine will be used to perform readings from the light sensor as well as the sound sensors in turn. We see here in the polling routine a sample loop which is used to continuously read inputs from the sensors, and this is performed using the get light reading and get sound level API routines. So in the get light reading routine, you will first initialize the register 0 to the light sensor port, and then call a standard sensor retrieval routine, which is the NX sensor analog get normalized, which is a polling based routine to read the value of the light sensor. We shall now focus on interrupt based I/O. Typically these are event driven, meaning that a hardware signal or else a timer expiration will trigger an interrupt, and this is used to initiate an I/O operation. So typically interrupt I/O is asynchronous because we cannot predict when the hardware signal will be received, or in terms of the timer expiry, depending on the hardware based clock, we do not know exactly when it will expire. So in order to perform some synchronization between the event that we are trying to detect and some other processing logic in our program, we will require the definition of rendezvous points. This means portions in the logic of the application that is used to make sure that the inputs that we are waiting for has been received and processed before we continue with the rest of the logic sequence. And the advantage of interrupt I/O is that it enables overlapped I/O, meaning that we can issue several I/O requests in parallel, and these can be processed in terms of the staggered processing approach in the kernel context. So how do we handle interrupts? As we mentioned previously, interrupts are asynchronous events, and when they occur and an interrupt handler is called, they would need to modify certain registers. Now these registers may be already in use by current process, and therefore we will need to preserve these process contexts when we initiate an interrupt handling routine. So secondly, interrupt handlers should execute quickly, because as we are executing an interrupt that is lengthy, this processing will block the handling of other interrupts. In order to avoid this lengthy processing issue, we typically will split the interrupt handling or processing into essential tasks. For example, copying the value of a status variable in the interrupt context into a memory variable location. And then, secondly, the background task that will actually take the inputs and process it and make use of it in a non-interrupt context. This is an example of an interrupt I/O pseudocode. We have a main program which would first set up the I/O request according to the following sequence. First, clear the I/O completion status variable, and then set up the I/O interrupt handler that will be called upon the interrupt, and then an IO command will be sent to the command control register of the peripheral, and while the command is being processed by the peripheral, we can continue processing other data if we like to. Finally, once we are ready to receive the reply from the peripheral, we will need to check the IO completion status variable if it is needed, and then to wait for the IO completion event, which is our rendezvous point. So the IO interrupt handler would first of all read the CSR of the peripheral and update the IO completion rate status variable once the interrupt has been triggered. Here we see the example of the NxOS interrupt handler in action. First, we need to initialize the SysTick handler. In this case, we need to install the interrupt service routine, or ISR, using the NxAIC install ISR routine. Here we specify the priority, the way that the interrupt is triggered, and the routine that will be called when it is triggered. So given in this initial part, there are two routines that are installed upon the initialization of the SysTick routine. So the important one that we will be looking at is the SysTick_ISR routine. After it has been installed, we will then program the PIT, or the programmable periodic interval timer, to trigger at a given rate. And this is done in the second highlighted block in this page. Here we see the example of a rendezvous point. Nx SysTick wait ms given a value will be called from the application and will wait until a certain duration timer interval duration has expired, and this is given by the SysTick value that we need to wait for. So in this routine, all it does is to loop while the value of the SysTick time is not equal to the value that we need. So here the SysTick time actually is a memory variable. However, it is updated by the SysTick interrupt routine when it is triggered. Therefore, this loop, although it looks like an endless loop because the values are referencing memory variables, it will exit once the timer interrupt has triggered and updated the value of SysTick_time such that it exceeds the required value. Here is the NX SysTick ISR routine. The interrupt handler routine in this case, the important part that is highlighted here is the part that updates the SysTick timer value in memory. So as we see, once the interrupt triggers, it will update the value in memory, and this is the value that will be read by the other routine used by the rendezvous point earlier. Next, we will look at interrupt nesting. Normally, interrupts are masked or disabled when we are inside an interrupt handler. So what happens with long execution time handlers is that they will block the servicing of other interrupts. One example of this is the LCD updating process, because we have to copy the whole entire display output buffer to the LCD peripheral. So in order to avoid such operation in the interrupt handler from blocking the more essential SysTick timer interrupt handler, we would need to have a way to allow the higher priority timer interrupt to come in and perform its task, and only then continue with the rest of the interrupt processing for the LCD display. Fortunately, the ARM has an advanced interrupt controller which supports 8 levels of prioritized interrupts. Because of this, the following interrupt sources have been prioritized such that the PIT, or the SysTick interrupt, has the highest priority. It will always has precedence over any lower priority interrupts. Secondly, the ARM AVR I2C link has a second highest priority because we need to have continuous communications with the AVR to maintain the operation of the NICT. If the NICT is not able to continuously communicate with the AVR coprocessor, the break will be shut down automatically by the AVR coprocessor after a timeout duration. So after the second priority for the I2C link, we have the hardware or peripheral interrupt, which are used to control the other peripherals in the microcontroller. The nesting of interrupts allow the servicing of higher priority interrupts while inside the lower priority interrupt handler. However, this leads to additional stack usage constraint because then we have to preserve the context of both the original lower priority interrupt as well as the context when we are inside the higher priority interrupt. This also leads to additional complexity and potentially deadlocks because nesting of interrupts is a rather complex procedure. We shall now look at how the IRQ handler is implemented in NxOS-Armdebug. First, these are the data structure definitions used for the interrupt handler. We have the interrupts count, which is used to determine how many interrupts are currently being serviced and nested. Secondly, we have the interrupt nesting level, which indicates the level of nesting that we are currently encountering. We start with -1 because there are no interrupts being active at this moment. A non-zero value will indicate that there is nested interrupts being active. Secondly, we may have additional debugging information to allow us to examine the interrupts process using the Armdebug processor or the JTAG debugger. This includes the stack frame address used to determine which is the interrupt stack frame that we are currently actively using, as well as any unserviced interrupts which is captured in the IRQ spurious count variable. The way that the NxOS-Armdebug IRQ handler works is that instead of performing the interrupt sequence in the IRQ context or the IRQ mode, we would use the original mode to execute the context. So example of this is that a user or system task would be executed in the system mode because we need to be in a privileged mode for executing interrupt handlers. Secondly, we will have the service mode or SVC mode, which is used for supervisor tasks such as the NxOS operating system itself. They will be again executed in the supervisor mode. Debugger tasks used by the Armdebug portion of NxOS-Armdebug will kick in the abort or undefined modes, and all these interrupt handlers will execute in the abort mode. Finally, all other reserved modes that are not handled will also default to execution in the abort mode for any interrupts. We would like to minimize register and stack usage whenever we are executing an interrupt handler. Consequently, as we note here, we only store certain registers that are modified by the interrupt handler. Registers that are not modified would not be stored at all on the stack. Examples of modified registers include the SPSR in the interrupt mode, the PC, the program counter for the interrupted instruction, the return register, register 12, and registers 3, 2, 1, and 0. First, when an interrupt occurs, it will invoke the NX_IRQ handler. The first thing we do when we enter into the interrupt mode or IRQ state is that we would like to keep the SPSR in a certain register because the SPSR would be needed later for restoring the context on return from the interrupt. In our case, we will use the stack pointer in the IRQ mode, which is R13, for storing the SPSR value. The reason we need to use R13 is because we cannot examine and modify the values in the SPSR directly. The other reason is that the stack pointer is not used in the interrupt state. So because of this, R13 is unused and we can use it as a scratch register. So in order to determine the previous mode, we use the mask for the mode values and determine what was the previous mode that was active. First, we will check for user and sys modes, and if it is previously in either of these modes, we will switch over to the sys mode in order to process the interrupt. If the previous state was not the sys or user mode, we will then check for supervisor mode and switch to supervisor mode if it was active. Otherwise, if neither of these states were active, we would switch to abort mode as the default state for processing interrupts. In order to process the interrupt, we must save the registers that we will modify. So in this case, we need to first of all allocate space on the stack. We shall use the specific interrupt handling mode stack pointer for performing this operation. So in the given mode, whether it's supervisor mode, abort mode, or sys mode, we will first update the stack pointer to allow us to store the number of variables or the registers that we have identified. Then we will store the user level registers R0, R1, R2, R3, R12, as well as the link register for the specific mode into the stack. Finally, we would need to update the stack pointer in order to point to the last two register positions on the stack for later use. You will need to return to the interrupted mode later. So in the meantime, we will store that CPSR value in R1. This will allow us to switch back to interrupt mode where we have the interrupted address in the link register value, as well as the SPSR that we have copied over previously. So in this case, we will set up the link register to point to the interrupted address, and the value to use to adjust the link register to point to the interrupted instruction address is defined in the hardware documentation. So we will copy the interrupted instruction address into R2 as well as the SPSR into R3 and store it into the stack at the top of the bank registers that we have stored previously. Now we shall perform some housekeeping used for debugging purposes. We'll update the nesting level, the stack frame, and miscellaneous other debugging information. Next, we need to program the AIC controller to allow for higher priorities interrupt to be re-enabled. After this, we will then switch back to the interrupted privilege mode in order to process the actual interrupt handler. Here, we will perform the call to the interrupt handler itself. Note that this interrupt handler subroutine is written as a normal routine, meaning that it is similar to any other subroutine written in the app user level program. This simplifies the programming and development of interrupt handlers for the kernel. So after we have called the subroutine and returned to the interrupt handler, we would then need to perform some cleanup. First, we would need to disable the interrupts from interfering from this critical section of code. We will then restore the link register value for the privilege mode that we are currently in, as well as the stack itself that should be cleaned up as to restore to the original value for the stack pointer. Next, we need to return to interrupt mode and to flag that the interrupt has been handled to the AIC in order for the same interrupt to be triggered later. Next, we'll perform some debugging information cleanup by updating the nesting level to reduce the level by 1. The next step is critical. First, we will need to restore the SPSR in the interrupt context to the original value so that we can return operation to the interrupted instruction later. So we will use the R1 as the register to load the SPSR value from stack and then store it back into the SPSR register for the interrupt state. Next, we will use one instruction, LDMFD, to retrieve all the user level registers as well as the new or interrupted instruction address into the program counter in order to resume execution of the interrupt instruction. And the caret at the end of this statement says that it will use the stored state in the SPSR to return to the execution state in the next instruction. Let's look at a comparison of these two I/O processing techniques. First, the polling technique has advantages in that it is easy to implement. Secondly, it has deterministic response time because we can pre-calculate the number of instructions executed to perform a certain I/O operation. Now, the disadvantage is that it is a blocking operation, meaning that once we initiate the polling command, it will not be able to process other tasks or run other instructions until the polling is completed. Therefore, it can also waste processing cycles, especially if we are waiting for a certain event to happen in the I/O sequence. Such applications of polling include batch processing, where we are not concerned about how long a certain operation will take, as well as for hard real-time applications, where the deterministic response time is an important criteria for ensuring that the system will function predictably. And in addition, in the kernel level, there may also be timing critical I/O sequence that will be called in interrupt handlers that will require a polling approach. On the other hand, interrupt-driven I/O provides fast response because it is only triggered when something happens. It allows for overlap processing because we can use different interrupt handlers to process different portions of I/O commands that take a long time. One example is the writing to the LCD as well as input and output on the USB bus. This may be overlapped by different I/O interrupt handlers. So events are driving the interrupt to trigger the interrupts, and therefore they are non-blocking because we can be performing other tasks in the meantime while we wait for an interrupt to happen. However, interrupt-driven I/O is complex. We need to preserve the context that has been interrupted, whether it's in user mode, in kernel mode, or within another interrupt handler if we are nesting interrupts. Secondly, we have to have status variables to indicate the completion of a certain event, and these status variables take up memory space. And finally, we will also need to have a completion routine, which will be called when the I/O process is done, so that the information can be conveyed to the user level program. The application of such interrupt-driven I/O is found in non-blocking I/O software, as well as for interactive and soft real-time systems. For more information regarding interrupt handling and nested interrupts, you can refer to the MSAMX Building Bare Metal ARM Systems with GNU, which is an online available resource for detailed explanation of how the interrupt process is handled by the ARM processor. Some of the NxOS-Armdebug source files that are referenced in this module are available in these references listed here. Until the next time, see you again.